All right, this is the first video in the section 5.6 on rational functions. Now, rational functions are called rational functions because what they are is a ratio or a fraction, like this, where you've got a polynomial on top and a polynomial on bottom. And I've got two examples down here. Both of these are obviously polynomials. But even if you had something like 1 over x squared plus x, that's also a rational function because remember, you can consider a single number to be a polynomial of degree 0. So let's look at these. First up, let's look at the domain. The domain is going to be all reals except for numbers that make the denominator 0. And sometimes there might not be any numbers that make the denominator 0, but you have to check. So if we look at these two examples, this first one over here, the denominator is going to be, the domain is going to be all reals except plus or minus 2, because positive or negative 2 will make this denominator 0. Now, if you look at the graph, you can easily see that here at 2, we've got a vertical asymptote, and so 2 is not in the domain. Negative 2, it's not obvious at all from the graph that it's not there. Because if we look back over here at the line negative 2, we're looking at the point right here on the graph. And that's not really there on the graph. Let me show you what I mean. If I take this and put it into Desmos, let's see, y equals x squared plus 5x plus 6. Put all of that over x squared minus 4. Zoom out a bit so we can actually see it. You can see that asymptote there. But if you look here at x equals negative 2, it's not really obvious that the graph doesn't exist there. If I click there and I drag down to get exactly on negative 2, you can see that it says negative 2 undefined. So that point is undefined and we really have an open circle here. All right, the domain, we just did the domain. The range of this would be all reals except for notice we've got this horizontal asymptote across here. And that horizontal asymptote happens at 1. So all reals except 1 for the range. All right, let's look at this other one. This one, if you look at the denominator, there's nothing that'll make this 0. X to the 4th plus 1, if you set it equal to 0, you get x to the 4th is negative 1, and that has no solution. So for this guy, the domain is all reals. Now the range on this one is difficult to find. Actually, we're not going to figure out what the range is. The range is going to, because notice this one has an asymptote as well at 1. Let's look at this one on Desmos and compare it. Let's see, 1 plus x on top, x to the 4th plus 1 on bottom. So if we look at this graph, if we wanted to figure out what the range was, notice this says 1.419. That's the highest value that it takes on. But that's not an exact value, that's an approximation. The exact value is going to be some irrational number probably. And the lowest value, I mean, you can look at it and see that it approaches 0 out this way. You can see that it approaches 0 going out this way, but it's coming from the negative side. So if we wanted the range, right now what we'd have to do is come down here and find the smallest value. Looks like Desmos found it there at negative 0.083. But again, that's a decimal approximation. So finding the range of these things, if it's a function like this, it's not something we're really equipped to do yet. in order to find that, you need some calculus, so you'll learn how to do that next semester. For now, what I want to focus on is on these types of graphs, let's find their vertical asymptotes and their horizontal asymptotes. So let's see, that's the next section. Horizontal asymptotes. Both of these graphs had a horizontal asymptote. This one had one at 0, and this one over here had one at 1. But let's look at how to find those in general. So what I like to do for my rational functions is I like to call them t over b. That way we have top and bottom. And I want to both give you the rules for how to find the horizontal asymptotes and try to do a decent job of explaining why those rules work. So let's think about this for a bit. Right now, just think about a polynomial, t and b. Think about them individually. When x gets big, either positive or negative, the value of a polynomial is also going to get big. That's because polynomials have end behavior where, on both ends, if it's even, both ends will either go up or go down. And if it's odd, one end will go up and down or the other way. But however it works out, if it's a polynomial, when x gets big, it's going to go up to infinity or down to negative infinity. It's going to be big in magnitude. And so that's the first thing. The second thing says, as x gets big, the non-leading terms of t of x and b of x become insignificant. Let's play with Desmos for a second on that. Let's just say I put in f or y equals x to the third. If I put in minus 3x squared plus x plus 10x plus 1, something like that. I want to change one of these to a negative to make it look a little nicer. Make the graph a little more interesting. But we've got this graph here. And as x gets big, the interesting thing is 3x squared, 10x, and 1, they become insignificant. Because when x gets big, that x cubed is going to grow so much faster than the other terms. It's going to be the boss that determines whether it goes up or down. So x cubed right now it's going up. If I put a negative on front, it's going to go down as x grows large. And as x grows large in the negative direction, right now it's going down. If I put that on there, it's going up. So really all we care about as far as what happens to the polynomial when x grows large is what happens with that, leading term. So the leading terms on the top and bottom, those are the only things that determine what happens to f of x as x goes to infinity. So let's play with this a little more. I'm going to put in a rational function. I'm going to put in x squared plus x plus 1 over x squared plus 3x plus 5. Now, if we look at this graph, there's some interesting stuff going on in the middle. But if you look way out, and we trace along here, this is getting close to 1. 9, 4, 9, 5, off the screen, 9, 6, and so on. If I change these values up here, well, actually, instead of doing that, let's just look at y equals x squared over x squared. Of course, that goes to 1. It's equal to 1. And this is, down here, this is the polynomial we get, or the rational function we get by just taking the leading terms of the top and bottom of this rational function. So notice if I put in a 3 there, this is approaching 3. Oh, let me get on the other function. This is approaching 3. If I put in, let's say I put in a 4 up here, and 2 down here. That means asymptotically, it's going to act like this function down here. And notice the red function is just 2, and the black function, if I can get a hold of it, it's approaching 2. So all we have to do is look at those look at the leading terms, and that'll tell us what happens. Let's come back up here. Right now, these have the same degree. And if I change this to x cubed, notice now it's going off to infinity. If I change this one down here to x cubed, now it's approaching 2. The y value, let me say it again, the y value of this function is approaching 2 as x grows large. And notice if I do the same thing over here and then I make x grow large in the negative direction, the y value here is also approaching 2. And these smaller terms down here, they don't matter. If I, let's say I change this to a 3x squared, it changes the middle of the function a little bit. If I change that to a 3x squared, or if I change this to a minus 10x. Doing that kind of stuff, it'll change the middle of the function, but it won't change what happens when x grows large. So all we have to do is look at the leading terms. Now let's look at this. What if this one down here had a higher degree? 2x to the 5th. Now x to the 5th grows faster than x cubed. So that makes this go to 0. And sure enough, we can even zoom in. You can see that this is getting closer and closer to 0 as x grows large. And if the top has a higher degree than the bottom, well, in this case, the top is going to grow faster than the bottom, and therefore it's going to grow to infinity. Now, if I change the sign of one of these, it would change it so that it grows to in this case, it's going to negative infinity. Might be kind of hard to see what's going on here. In this case, we've got a vertical asymptote somewhere in here, and then we've got the graph going to negative infinity as x grows to infinity. So let's go back and look at the rules. These facts here. Remember, t is the top and b is the bottom. If the degree of t is larger, the graph has no horizontal asymptote, because as t goes to infinity, t of x grows faster than the bottom. And so you're going to go to positive or negative infinity, just depending on the signs of the thing. You can think of this as like a race between the top and bottom. You've got a fraction when the top gets large, that makes the number large. When the bottom gets large, that makes the number close to 0. So it's really a matter of which one's growing faster. And in this case, the degree of t is larger, the top's growing faster. If the degree of b is larger, then you get 0 as a horizontal asymptote because b is growing faster. And if they have the same degree, then what you get is a horizontal asymptote here where y is the ratio of the leading coefficients. So that's a lot of explanation. And after doing that, I think we can run through these examples fairly quickly. If you want to, pause before each of them and work them out yourself and then check. Okay, let's see. This one, we've got, I'll do this in purple. Let's see. The leading coefficients are here, leading terms. The bottom has a greater degree, so y equals 0 is the horizontal asymptote. Okay, down here, we've got the same degree on top and bottom, so the horizontal asymptote is going to be y equals 5 over 10 or 1/2. All right, on this one, let's see, this is the leading term and this is the leading term. So for this one, the horizontal asymptote is going to be y equals -1. When you do these, be sure to grab the sign as well as just the number. All right. For this one, let's see. We've got the top has x cubed and the bottom has 3x squared. So the top here grows faster. So this thing has no horizontal asymptote. And in fact, what would happen here, when x grows large, the top here is going to outrun the bottom. And since they're both positive, this would go to positive infinity as x goes to infinity. All right.